Okay, hi guys, welcome back to another video on IMONST. So in this video, we'll be talking about junior question 10 to 13, and for seniors, it'll be question 5 to 8. Okay, so let's start right away. So in problem 10, we can see here Farah received a calendar for year 2020 as a gift. Once the year ends, she plans to keep it because she can reuse the exact same calendar in a future year N. This means for any given date in the year N, it will fall on the same day as in year 2020. So what is the smallest possible N? So note that there are normal years, right? Normal years. I forgot the exact term, but so normal years and leap years, right? Leap years are the years in which such a day, 29th of February, exists, and then normal years are when that day does not exist. So leap years are in multiples of 4 normally, right? Because of the Earth's rotation around the sun, then you need to count one extra day. So normally these are multiples of 4. So like 2016, 2020, 2024, and then 2028, and so on and so forth. So if this Farah wants to use the calendar in the future, and then she wants to have it in like every day is the same, she can only see leap years because all the normal years like 2022, 2023, which are not multiples of 4, don't have a 29th February, so she can only see these. Right? And then let's see from say 2020 to 2024. Okay, I don't know what the first January of this day is, but I can search. I don't know. Give me a moment. Okay guys, I just searched that the 1st of January of the year 2020 is actually a Wednesday, so that's okay. And then for normal years, we know that, okay, so let me know. So for normal years, and we have 365 days, which is equals to 52 times 7 plus 1. Okay, 7 meaning 7 days in a week, and then 52 weeks, extra 1 week, extra 1 day out here. And then for a leap year, we will have 366 days, which is 52 times 7 plus 2. So extra 2 days. So let's say, okay, let me move. Okay, 2021, 2022, so 2023, and then 2024. So if on 2020, the 1st of January falls on a Wednesday, so 2021, it will land on, because this is plus 2 days, it will be on a Friday. And then for this one, because it's a normal year, so we just plus 1. This one will be on a Saturday. And then this one, since this is also a plus 1, this will be a Sunday. And then for this one, this is also a plus 1, so this is a Monday. So as you can see here, from one leap year to the next, we add 5 days, right? But since we want to say, let me think. Okay, since Farah wants to reuse the same calendar in a future, which we know is a leap year already, where if the 1st of January is a Wednesday, and then that year the 1st of January will also be a Wednesday, so the number of plus 5 she will have to take would be a multiple of 7, so something like this. Okay, so for these, since 5 and 7 are co-prime, meaning that they do not share any common factor other than 1. So 2020, we will need to add like 7 times 4, because once every 4 years would be 2048. So 2048 is the smallest possible N that Farah can use a calendar, but like, I don't know how old Farah will be, okay? So this is the answer for problem 10, which is 2048. If you guys think that I do not explain well enough, you can ask me further questions in the comments, okay? So we have a problem 11. This one we will need to exhaust, okay? So a positive integer is defined as awesome if the sum of its digits equals its number of digits. So for example, 2020 is awesome because its sum of digits and number of digits are both 4. How many awesome positive integers, including 2020, less than 10,000 are there? Then an awesome integer cannot start with digit 0. Okay? So if it's less than 10,000, the maximum number of digits, is 4. Maximum 9999, right? Because less than 10,000, right? So we will separate these into 4 cases. So if like so 1 digit, then 2 digits, then we have 3 digits, then finally 4 digits. So we need to exhaust all of them. We need to find all of them out. Okay, so this is basically just listing, and I don't think there's really another way. So if you guys do have another way, you guys can write it to me in the comments as always. So I'll just list out all the numbers for you. So for 1 digit, the sum is 1, so there's only 1. There's no other unit digit actually. So there's only one case in this there's only one case in this particular situation. And then for 2 digits, the sum is 2. So the smallest one is 11, and the largest one, which is the only second one, is 20. So there are only 2 of them, right? So for 3 digits, the sum is 3. So the smallest one we can make is 102, and then the next one is 111. Then we have 120. So this is if the hundredth digit is 1. Then if we have a 2 at the front, then we'll have 201 and then 210. That's it. And then we have finally 300, because this is 3 and then it maxed out all the sums, so the back can only be 0. Okay, so in this case, in this situation where we have 3 digits, we'll have 6 cases. So for 4 digits, we would have quite a long list, but bear with me. So 4 digits sum is 4, right? So the smallest one is obviously 1, starting from 1. So 1003, then 1012, 1021, 1030. Okay, and then if our hundredth digit is 1, so 1102, 1111, 1120. Then if our hundredth digit is 2, 1201, 1210. Then if our hundredth digit is 3, 1300. So if the thousandth digit is 1, we have 10 cases. So make a small mark here. And then for 2, as the thousandth digit, we'll have 2002, 2011, 2020. And then we have 2101, 2110, and then finally 2200. So we have 6 cases here. Also take a small note. Then if our thousandth digit is 3, we will have 3001, 3010, 3100. So 3 cases. Then finally 4 as the thousandth digit. So since the sum is only 4, so 4000 is the only case here. So 1 digit here. So in the situation that we have 4 digits, there are like 20 cases in total. So you need to list them all out and then double check to ensure that you have not left something out. So adding up 1, 2, 6, and 20, in total there are 29 cases for this. Okay, so the answer to problem 11 is 29. Hope you guys understood my solution, and we'll move on to problem 12. Okay, now find the last digit of the number of this bunch of brackets. Okay, so of course we need to start with the innermost, and then let's gradually move outwards. Okay, so here's a small fact. So for last digit of any number, you can do mod 10. If for people who already know what mod is, but if you don't know, you could check out one of my videos. I put like a link I'll put a link on the upper right corner, but I'm sorry because if you can't speak Chinese, because I recorded the video in Chinese, but I'll kind of briefly explain mod in my future videos. Okay, for now let's stick to a more traditional way. Okay, so for the innermost, we have 1 plus 1 to the power of 10, right? So which is 2 to the power of 10. Then since we want to look at the last digit, let's look. So let's kind of make a small graph, okay? So let's say this is 2 to the power of n and then the last digit, right? Okay, so for n equals to 1, we have 2 to the power of 1. Okay, wait. Okay, so let's add another column. So for n equals to 1, 2 to the power of n is 2, last digit is 2. For n equals to 2, 2 to the power of 2 is 4, last digit 4. For 3, no need to say. For 4 is 16. Now, we only want last digit, so this is 6. So for n equals to 5, we have 32, and then so the last digit is 2. For 6, 2 to the power of n is 64, and then the last digit is 4. Okay, so as you can see here, there has already been like a cycle, right? So the next cycle will repeat the same. So there are 4 terms per cycle here, as we can see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for 10, so 2 to the power of 10 will have the same last digit as 2 to the power of 2, which is 4. So we have, okay, so we have here 4 plus 1 to the 20th power, and then plus 1 to the 30th power, then plus 1 to the 40th power, which is still quite a mess, but let's kind of tackle it slowly. So we have 4 plus 1. We can ignore the front part, or what the tens digit are. The tens digit is, the hundreds digit is, the thousands digit is. It's not important in this question. So you can see here 4 plus 1 to the power to the 20th power, so which is 5 to the 20th power. Then let's make another thing. Let's make something like previously we've done. Okay, so last digit. Then we can see for n equals to 1, we would have 5. You have 5, and then for 2, 25, 3, 1, 2, 5, 4, 6, 2, 5. The last digit is always constant. It's always a 5, right? As you can see here. So even if I put to the 20th power, it will still be a 5, right? Okay, so let's move on. We have 5 plus 1 to the 30th power plus 1 to the 40th power. Then we can see here this is a 6, right? So let's do this for 6. Then I'll abbreviate the last digit with LD, as you can see here. So I hope you can understand it. So n, so 1, 2, 3, 4, 5, right? Okay. So we have 6 to the power of 1 is 6, 6 to the power of 2, 36, 6 to the power of 3, 216, 6 to the power of 4, 1296, 6 to the power of 5, 7776, and then you can see all the last digits are still 6, and this will continue indefinitely. So we can move this down. We can become something like a 6 plus 1 to the power of 40, so which is 7 to the power of 40. So let's check for 7. So this is a more traditional way. If you know how to do mod 10, then congrats. This would be quite a kind of like a warm-up question for you. So this is n, 7 to the power of n, and then the last digit. Okay, so for n, 1, 2, 3, 4, 5, 6. Okay, for 7 to the power of 1 will be 7, 7 to the power of 2, 49, 7 to the power of 3, 343, and then times 7, 2401, 16807. 117649, something like this, right? Okay, so we can see here the last digits are respectively 7, 9, 3, 1, 7, 9, 3, 1, something like this, right? So it also where's my pen? So this one also recurs in cycles of 4, so like 7, 9, 3, 1, 7, 9, 3, 1, right? So since it occurs in periods of 4, so let's find the remainder of 40 when divided by 4, which we can see is obviously 0, so it's a multiple of 4, so it's the 4th, so it's the same as the 4th term. So for 7 to the power of 40, the last digit LD is equals to 1, and our answer for problem 12 will exactly be 1. So you can confirm it by doing it yourself. Of course, doing it yourself, doing all these questions yourself beforehand is a better way, and then just use my videos as a reference. Okay, so now we arrive to the last problem of the day. So we have problem 13 here, and problem 8 for seniors. So let A, B, C, D, E, F be a regular hexagon. Then lines AC and BE intersect at G. There are no hexagons. I guess I'll need to draw one myself. Then determine the value of, okay, let's draw one first to not make this so confusing. So a regular, I'll draw something as close as possible to a regular hexagon, because using drawing is not that possible. So say anti-clockwise. So this is a regular hexagon, and then lines AC and BE intersect at G. So if they intersect at G, it's here. So determine the value of the area of AGE. So we want this. And then to the area of BCG. So what's the area of this? So as you can see here, this is a 90 degree. As you can see here, you can draw it out also. So this is 90 degree, this is 90 degree. And then since since this is a regular hexagon, right? So these 6 sides are all the same. So if we cut it by half, this is like an angle bisector, and then we would have AG being equal to GC. So since we have AG equals to GC, let me use a new way of notation. So let's denote, so say this middle bracket AGE to be the area. Okay, so area of triangle AGE. So again, so for middle bracket BCG is also the area of triangle BCG. Okay, so since these two, we can consider these as the same height. So we can say, let me think. So since they share like a common height, the area of AGE and BCG is equal to the ratio of their lengths, because this is like a 90 degree, so it's just like a base times height divided by 2 thing. So okay, base times height divided by 2. Okay, so AGE over BCG would be something like GE over BG. Okay, something like this. Okay, sorry, I forgot that I have left out an important detail. So for this regular hexagon, each angle will be 120 degrees. I'm sure most of you guys know this already. So if you don't know, this is like a quick reminder. And then if I cut this, so let me magnify this part. So this part, we have a 90 degree. Then we have a 60 degrees here, and then a 30 degrees here, which is exactly half of an equilateral triangle. Okay, so as we can see here, so let me see. Okay, so this BE line, right, and this AF line. Okay, let's see. Give me a moment. Now this where's this this area BCG is basically the same as area BGA. Okay, so we're just flipping this up, so we have something here. Sorry if my picture is very messy. You guys might have to make do with that for some moment. Okay, so we have our G here, and then maybe create a point H here, right? So basically this trapezium ABEF, right, can be divided into 3 equilateral triangles, because hexagons can be divided into 6 equilateral triangles. So you can see here, here's like a B, and then here's a 2B, 2B, 2B. So B maybe being a base, I'm not sure. Okay. So we can see that our triangle AGE has 3B, then our triangle BGA, which is the same as BGC, has 1B, right? So the area of triangle AGE over the area of triangle BCG would be 3B over B, as you can see here, which is 3. So the answer for question 13 is 3. I hope I explained it well, and then there are no like questions. So if you guys still have any questions, of course you can still write down in comments. Okay, I'm sorry if I kind of mess this explanation process up. Still learning. That's all for today. So for the next video, we'll be discussing problems 14 to 17 for juniors, and then 9 to 12 for seniors. Okay, see you next time.